Go. Let's look at sample test number 4 for Physics 224. A substance has an index of refraction of 1.84, which is the closest to the speed of light through it. Alright, so the speed of light is related to index of refraction as so. So the fastest speed of light is when n equals 1. That's the smallest n can be, and that will give velocity is the speed of light. But if in other things, not vacuum, then the speed of light will be slower, and so we divide by n, which is something bigger than 1. So in this case, n is 1.84, so we're going to have the speed of light 3.0 times 10 to the 8th meters per second divided by n, 1.84. So this velocity comes out to be 3e8 divided by 1.84. 163 times 10 to the 6th meters per second. So that would be 1.63 times 10 to the 8th. And looks like D is the closest. Alright, speed of light. Speed that light travels through a material depends on the light's color. True or false? Yes, because colors have different wavelengths, and index of refraction depends on n depends on lambda. So that's true. If the magnification of a lens is negative 5.9, we know that. Well, remember, if the magnification is negative, that means it's upside down, inverted. And if the magnification m is greater, magnitude of the magnification is greater than 1, then it's larger, or the image is larger, magnified. And so this one is, the image should be larger and inverted. So upright, no. Closer to the lens than the object, no. So m is also negative di over do. So di over do is bigger than 1, so di is farther away than do. So that's wrong. The image is larger than the object, yes. This is that's not. So the answer is C. Number 4. A ray of light strikes a diamond with an index of refraction 2.42 at angle 25. Find the angle of the ray that is reflected. Alright, so that's the easy one, right? Angle of incidence here, theta I, is equal to theta r. Right? And so theta r reflected equals 25 degrees, which is theta I. Okay. B. Alright, ray of light strikes a diamond. Find the refracted ray with respect to normal. Alright, so now we need Snell's law. So we'll say n of air sine theta air equals n of diamond sine theta diamond. And we've got n of air is 1. Theta in the air is 25 degrees, n of the diamond is 2.42, and so we got sine of 25 degrees equals 2.42 sine of theta d, so we can times 1. So solving for theta d, divide through by 2.42 on both sides. So this cancels, and then we're going to take the inverse sine, so we get theta d is inverse sine of 25 divided by 2.42. So theta d is, I hate it when I do that. Okay. Inverse sine of 25, and then not the 25 divided by 2.42, but the whole thing divided by 2.42. There we go, that looks good. 10.1 degrees. So we'll go with A, 10 degrees. When the reflection of an object is seen in a plane mirror, the image is, so a plane mirror, it's just a flat mirror, right? So the light comes straight back, or reflected rays. Anyway, so the image looks like it's coming from back here. We're all used to looking in a mirror. We look like we're right side up and we're behind the mirror, right? So it's virtual because this is the light side for a mirror. This is the dark side for a mirror. The light doesn't actually go there. And so it's on the dark side, so it's virtual, and we aren't upside down in the mirror, so it's B. The image formed on the retina of a human eye is always, so you've got the eyeball that has the lens. Remember, it's a converging lens, and so you got an image. It's going to come in parallel and then go through the focal point. Sorry. And ray number 3 is going to go something like that. Oops. Start over. What a mess. Got our eyeball with a lens. Got an image out here, or an object out here. And parallel, go through the focal point down there. The one through the center. And something like that. So the image is going to be over here. So it's supposed to be on the retina there. So it's going to be inverted, and it's going to be the light's going this way. And so this is a real image back in here where the light's going. So it's real, and it's small, and it's inverted. D. White light is sent through a prism. The various colors are separated in typical fashion. We call it diffraction, or dispersion, I'm sorry. Dispersion. That's not the question. Which of the following colors would have the lowest index of refraction in the prism? All right, so which basically is just asking which color has the lowest index of refraction. In general, the order goes in the normal way. And so let's think about this. So I guess in general, we know, or we can look up, or you can have written down that the index of refraction for red is less than yellow, is less than blue. But say you didn't have that written down, how could we figure this out? Remember when we were looking at the critical angle in lab, which color disappeared first? And critical for blue was smaller than for red, right? Red disappeared last, blue disappeared first, and the equation for the critical angle is inverse sine of 1 over n, or n 2 over n1. And so basically this n that we're talking about for the material is where what these would be is in the bottom. And so a smaller index of refraction would have a bigger critical angle, right? So red had the bigger critical angle, so it must have the smaller index of refraction. So lowest index of refraction is red. All right. White light is sent through a prism. That's the same question we just, or no, maybe not. No, it's okay. We have a different, which one is the smallest critical angle? Let's go back. Sorry. So, like I was just talking about in the stuff we had before, as we played with it in lab, we turned it, the angle was getting bigger and bigger. First blue goes away, and then yellow, red, yellow, green, red. But actually violet is before blue, right? And the spectrum on the rainbow, you got violet, blue, green, yellow, orange, red, kind of thing. And so it should be A. Sorry, my dogs are making noises. Okay, 10. If you look through 2 lenses at once, okay, so 2 of them in a row, one with magnification of -5 and one with magnification of 0.5, what would you see? So what is the total magnification, first off? It's what we need to figure out, and we just multiply the magnifications of the 2 pieces. And so it would be -5 times 0.5. So the total magnification would be negative 2.5. So again, it's negative, so that means it's inverted. Inverted. And this is magnitude of m is greater than 1, and so it means the image is larger than the object really is. Okay, so it looks, so we've got inverted and larger. There we go, first one. Okay. In Young's double slit experiment, both the distance to the screen and the slit separation are decreased by 50%. Distance to the screen is what we call L, and the slit separation is what we call D. What happens to the distance between adjacent bright fringes? Alright, so we had sine theta is, well, d sine theta is m lambda for bright fringes, full wavelengths. And so sine theta, we had m lambda over d. To get the y, we had tan theta was y over L, or y is L tan theta. And we use the approximation sine theta is about tan theta. So we ended up with y was L sine theta, but sine theta is this, m lambda over d. Okay, so y sub m, we're looking at the different bright light parts. We call them fringes, I guess. So this was m equals 0, 0, m equals 1, negative 1, so forth. Okay, question is, D and L both become 1/2 of what they were. Then what happens? Well, nothing happens because the one's on top, one's on the bottom, so the 1/2s cancel out. So it stays the same. Okay. If a wave from one slit of the double slit setup arrives at a point on the screen 1 full wavelength behind the wave from the other slit, what is observed? So a full wavelength. So one gets there here, the peak happens there, and then the next one, its peak starts a full wavelength behind, but they're still totally lined up. If they were half, it would be the destructive interference, but this is still constructive interference. They both are peaking at the same time, just technically one wavelength behind, but they're still lined up, so it'll be bright fringe. As we saw in lab, which color of light has the smallest critical angle for total internal reflection? Didn't we just do this? Smallest critical angle. Anyway, we saw that the blue went away first, so D. Under white light, an object appears blue. So under white light, so all the light's there, all the different colors are there. It looks blue with cyan writing. All right, so cyan, remember, is blue and green together. If the light source changes to green, what will be the appearance of the color scheme? Okay, so our eyes have can only see certain colors. It's a green, so with the light source is green, there's only green light going, and so the blue thing will absorb all of it. There's no green, all the green gets soaked in, no blue to bounce back, so the blue part will appear dark, so it's one of these two. And then the cyan does have some green in it, so when the green light shines on, the green will come back, and so it'll be dark with green writing. All right. Which of these are not correct ray diagrams for a converging lens? All right, so converging lens, parallel rays have to come to the focal point. Parallel from the other side has come to the focal point, so that looks okay. So I think this is okay. This is a converging lens, but look at this parallel ray is coming and is diverging. It's going away from the focal point. It should be going in. So this one is bad. So this is a bad one. B. Same kind of thing here. So even if it's going one way, we can look at it, think of it going backwards. It still should be any parallel ray when it comes to the other side should be going to the focal point. This one looks like it's going away instead of going in or coming from away. And so this one is bad. So C is bad also. Let's see. So this just kind of looking at it, parallel to focal, that's good. Parallel focal, that's good. Through the center, that's good. I think that one's good. So this one's parallel to focal, but this one is doing something crazy. It's got to go through the lens, right? So this isn't right. I guess it's trying to go there and go through the focal point there. All right, so E is messed up. So B, C, and E are the ones that are messed up. Okay, I guess I should check myself, make sure I'm agreeing with myself here. 3 A's, B, D, B, B, C, and E. B, A, C, B, A, D, B, A, B. Okay, looks good. Number 16. Consider a ray of light incident on thick glass container full of water. Angle of 40 degrees is shown. Find the angle of refracted ray as the light enters the glass from the air. All right, mark this as theta 2. So this is the angle, theta 2, of the refracted ray. So here's a perpendicular. This is the incident at 40 degrees, or theta 1. Let's call the air theta 1. So N1 is 1. N2 is here, and 3 is here. So N1 is air, N2 is glass, and 3 is water. Okay, so there's theta 2. So refracted ray means Snell's law. And we've got 1 and 2, so we'll do N1 sine theta 1 equals N2 sine theta 2. N1, so N1 is 1. Sine theta 1 is sine of 40 degrees. N2 is 1.5. And sine and theta 2 is what we're looking for. Divide both sides by 1.5. And then take the inverse sine. So theta 2 is inverse sine of 1 over 1.5 times sine of 40 degrees. Inverse sine of, let's put it in parentheses just to be safe, 1 divided by 1.5, and then get outside the parentheses, so I did some little parentheses here, times sine of 40. Looks good. 25.4 degrees. Looks good. That's theta 2. Determine the angle of the refracted ray as light enters the water from the glass. Water from the glass. So now we're in here, and so the refracted ray would be here. It says to call it theta 3. Theta 2, the incident angle, is always with respect to perpendicular, so that's the angle here. But since we've got two parallel lines, and these are alternate interior angles for a line cutting the two parallel lines, this is also going to be theta 2. So we are good here. So we can do another Snell's law. So N2 sine theta 2 has to be equal to N3 sine theta 3. N2 is 1.5 sine theta 2, which we just got, is 25.4, equals N3, 1.33. Sine of theta 3 is what we're looking for. Again, solving, divide by 1.33 on both sides. And then do the inverse sine. So theta 3 is inverse sine of 1.5 divided by 1.33, and then times sine of 25.4 degrees inside of the inverse sine. All right. Inverse sine of, let's put some parentheses, 1.5 divided by 1.33, and then multiply that by sine of 25.4 at 28.9 degrees for theta 3. Alright. Determine the critical angle for the glass to water boundary. So we're talking about right here. Light's coming in, and what's the biggest angle? Or what does angle, I guess the smallest angle. Anyway, the smallest angle that causes the light to, basically when the angle is here, when the light that gets in the water ends up being 90 degrees, and so then it's all going to, after that, when you get bigger than theta critical, it's all going to be inside, right? And so in general, we have the formula sine of theta critical equals n2 over n1, or theta critical is inverse sine of n2 over n1, where n1 is where the light starts, n2 is where it ends. So in this case, it's starting in the glass. We're looking for the total internal reflection in the glass. So n1 is n glass. So theta critical is inverse sine of n, it's going to the water, we said, so n water over n glass. N glass. Alright, so total internal reflection is not possible if, when we try to put these things in, the n values in, we are trying to take inverse sine of something bigger than 1, and we know sine can never be bigger than 1. So theta critical in this case is inverse sine of water, and water is 1.33, and glass is 1.50, so we're okay because the top is smaller than the bottom. So we'll do inverse sine 1.33 divided by 1.5. 62.5 degrees is theta critical for glass to water. Okay, next one, find the critical angle for glass to air. So now we're wondering about over here, what's the angle that makes it start coming back in and be all reflected over here. So again, same formula but different ends. We've got inverse sine of, where is it going to this time? Air. So n air, and where is the light starting, or where is the light basically staying, is in the glass again. Alright, so inverse sine of, and air was 1 and glass is 1.5, so again we're good because the top of the fraction is smaller than the bottom. So theta critical glass to air is inverse sine of 1 divided by 1.5, 41.8 degrees. Okay, find the reflected angle for the light entering the glass from the air. Sketch the reflected ray on the picture. So reflected is the bouncing off like a mirror kind of reflection, right? And so something like this, the light comes in and is reflected off, and this would be theta reflected right in there. And we know from the law of reflection, theta reflected equals theta incident. In this case equals theta 1, which is 40 degrees. So theta reflected is 40 degrees. Okay, so there's a reflected angle, and we drew it on the picture. Okay. Let's look at number 17. Consider a converging lens, focal length of 5 centimeters, the object placed 3 centimeters to the left of it. Where is the image? Okay, so focal length, converging lens, focal length is positive, so f equals 5 centimeters. And the object is 3 centimeters, so we say DO is 3 centimeters. Where's the image? So we're going to use the lens equation. 1 over f is 1 over DO plus 1 over DI. It says where is the image, so that's asking what is DI. Alright, so DI, solving this equation, subtracting 1 over DO from both sides and then taking 1 over to get DI on top. We're going to do 1 over F minus 1 over DO. Okay, 1 over 5 minus 1 over 3. So everything is in centimeters here, so we're okay to leave it in centimeters and our answer will be in centimeters. So 1 divided by, get opening parenthesis, 1 divided by 5 minus 1 divided by 3. Looks good. Negative 0.7, not negative 0.7, negative 7.5. Negative 7.5 centimeters. All right. And so the image, we got negative DI, so the image is on the dark side for your lens. So use a straight edge to draw a ray diagram below. Use the dotted line as the position of the lens. Be sure to include focal points. Some books call them SO and SI. We'll call them DO and DI here. The lens shape. So it's a converging lens. Converging lenses are fatter in the middle. All right. That's supposed to be a converging lens, kind of uniform, fat in the middle. Okay. The focal length is 5 centimeters. We'll just take these as centimeters. So 1, 2, 3, 4, 5. So this is F, and then also over here 1, 2, 3, 4, 5. So we got 2 focal points for lenses. This is also F, little f. So we labeled the focal points with capital letters, capital F, but the distance is little f. And we've got the object is 3 centimeters to the left, so we go 1, 2, 3. So here, we'll just draw a little object here. This is our object. And so then the distance here would be, whoops, 3 centimeters to the left of the lens, not left of the focal point. Wrong. 1, 2, 3. So the object is here. And then this distance is DO, 3 centimeters. Okay? DI is negative 7.5, so it's on the dark side. Where is dark side on this lens? Dark side is where the light goes after it hits the lens or mirror. Or no, the light side is where it goes after it hits the mirror. So this side is the light side. This is the dark side. So this is a virtual image because DI is negative. It's on the dark side. It's negative 7.5. So 1, 2, 3, 4, 5, 6, 7.5. So we should get DI to be over here if we draw our picture right. It might be a big if, but we'll try. Okay. So we've got, we'll start with, where's my ruler? Here we go. Ray number 1, parallel focal. All right, so we start off from the tip going parallel till we hit the lens, and then it's converging lens, so then it would, if when it goes through, then it has to go converging. All parallel things have to converge to the focal point and go on down here, something like that. So that's ray number 1, parallel focal point. Ray number 2 is focal point parallel, right? So we can do one like this, coming from the focal point, going to the tip, going to the lens, has to go to the lens, and then once it hits the lens, it goes parallel. Something like that. Something like that. So that's, yeah, they're on top of each other. My number is in the way here. So here's lens number 1, or ray number 1, ray number 2, and then ray number 3 goes through the center. Again, my number is in the way, but let's just go with it. So this would be ray number 3 going through the center. So this is 3. This is 1. Okay, we've got our 3 rays. Now we've got to look where they appear to be coming from. And so we've got to kind of extend these. They're all going out this way. We've got to figure out where they would go together. Back here. This is not looking good here. Whoops. I didn't go to the focal point on that one. I went to, I don't know where I was going. Got to go to the focal point. Parallel focal point. So we got to go to the focal point here. After it, parallel focal point. That's going to help. Come back here. So it looks like they're coming from back here, and they all come together. Oh, let's say it's about here where they're supposed to. It's supposed to be negative 7.5, so if we use our imagination, they almost look like they're coming from this way if we extend them back as if the lens weren't there, right? All right, so our image should be here. Okay, D image is supposed to be negative 7.5. So we've got focal points, yes. We've got DO and DI, yes. We've got F, yes. Lens shape, yes. 3 rays, yes. Image and object, yes. Okay, so we did that part. All right, calculate the magnification of the lens. So we got M could be negative DI over DO or HI over HO, depending on what we have. We don't have anything about the H's, so we're going to use negative DI over DO. Negative 7.5 centimeters over DO was 3 centimeters. So it's good kind of to use, make sure we get the units, make sure they're the same units, so that's good. So we got 7.5 divided by 3. 2.5, yes. 2.5 is the magnification, and we had negative and negative, so it is a positive magnification. So we would expect the image to be upright and larger than the object. Yay, it is upright and larger than the object. Good, okay. If the object is 10 centimeters tall, I didn't draw it 10 centimeters tall, but we didn't know. We'll pretend we didn't know anyway. So HO is 10 centimeters. Then how tall is the image? So now we can use M equals HI over HO, or rearranging, that says HO is M times HI. So, I'm sorry. No, it isn't. HI is M times HO, H sub O, hi ho. Okay. H sub, multiply both sides by H, yes. Okay, so HI is 2.5 times 10 centimeters. So HI would be 25 centimeters in this case. Okay. Okay, so could just as easily make the lens problem be a diverging lens, then F would be a negative number, but still draw the rays the same way, use the same kind of equations, something like that. Let's look at the next one here. Convex mirror, radius of curvature. Okay, 10 centimeters. Image appearing 4 centimeters behind the mirror. Excuse me. And so radius of curvature, that's giving us R, is 10 centimeters. And image behind the mirror, so means that DI is negative 4 centimeters. It's on the dark side, right? So it's a virtual image. Virtual image, negative DI. Okay. We can get R from F, F from R, remember, for mirrors, or anyway, we can get F from R by just dividing by 2. So F is 5 centimeters, but it's a convex mirror, so it's actually negative 5 centimeters. All right, because we've got, let me just draw it here. convex mirror. Right, so if the object is over here, it's bulging out, the radius of curvature, to make a big circle, the radius is over on this side, right? And so in this case, 1, 2, 3, 4, 5 is the focal point. Actually, it's probably supposed to be from the mirror, not from that dotted line. So let's just say it's going through here. So 1, 2, 3, 4, 5 would be the focal point. So it would be the focal length 5 or -5. Getting ahead of myself. Where is the object? So we're going to use the lens equation, mirror equation are the same. 1 over f is 1 over do plus 1 over di. Oh, yes, but we're looking for the object this time. But it's the same math. So do, we're going to subtract di from both sides and then take 1 over everything. So 1 over f minus 1 over di. All right, so 1 over -5 minus 1 over di is -4. All right, 1 divided by opening parentheses, 1 divided by -5 minus 1 divided by -4. Lots of negatives in this one. If your calculator shows you your equation again, it's good to just double check to make sure we got everything right. Looks like I did. And so we get do is 20 centimeters. So the object, shoot, okay. I don't think I have 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll have to make each one of these 2. So I got a little carried premature on drawing my picture here. So the object, so let's call each of these 2. So this is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 2, 4, 6, 8, 12, 14, 16, 18, 20. So this is 20. This is do is 20. The object is here. All right, so each of these is 2. So 2, 4, 5 would be here for the focal point then. Changing our scale a little bit, because we're going to sketch the ray diagram again. Dotted lines, position of the mirror. Be sure, yeah, I should fix those. do and di, f, lens shape, 3 rays, image and object. Okay, so the image, we say, is 4 centimeters behind the mirror. So we got 2, 4. So the image is back here. It's supposed to be. We don't know how big it's going to be, so I probably have to change that. But it's supposed to be back here somewhere. So this should be di. Hopefully. All right. So let's draw the ray diagrams. So starting with the object. Let's make it go up to this little line here so you can see what parallel is. So parallel is here. And then it bounces off. So ray number 1, write my 1 here, is parallel focal. At least mirrors only have 1 focal point, so that's easier maybe. Something like that is ray number 1, parallel focal. Ray number 2, focal parallel. So it tries to go to the focal point, but it gets reflected off. It has to go parallel. Even with a ruler, it's a little hard to tell what's parallel even. Okay, so this is ray number 2. And then finally ray number 3 goes through the center and then comes back down the same. So if that was up to there, it should be down to here at the same distance. Connect the dots a little bit. something like that. So this one is number 3. Okay, so now we got to look at the light that's coming out. Where does it look like it's coming from? So we got to go back, continue these lines back, lines that are coming out at us on the light side. See if they cross. Hope they cross somewhere where they're supposed to. Alright, so I made my image a little tall, but looks like they cross almost where they're supposed to. My image is down here. Here's the little guy, and this DI is supposed to be -4, so it's pretty close. Okay, so we got DO and DI, we got F, we got the lens shape or the mirror shape, 3 rays, image and object. Good. Okay. Part C, calculate the magnification of the mirror. So M, again, -DI over DO, since we don't have information about H's. So -DI is -4 centimeters. DO is 20 centimeters. So it becomes negative and negative, so 0.2 is the magnification. It's a plus. Okay, so it should be smaller because M is less than 1. Magnitude of M is less than 1, so it should be smaller. Image should be smaller, yes. And it's positive, so it should be upright. And yes, it is. It's upright. Good. Okay. Yay. So part D. If the object now is 10 tall, how tall is the image? So this is just like what we had before. So M, HI over HO. So HI is MHO. So HI is M, which is 0.2, times HO, which is 10 centimeters. So HI is 2 centimeters. Okay. Why did I get it? I don't know. Yes, good. Okay. One more problem looks like. Consider the double slit setup with 600 nanometer light. So 600 nanometer is our wavelength, lambda. The screen is 2.5 meters away from the slit, so that is our distance. I think we call it L. And it says, find the slit separation needed to make the second bright maxima 25 millimeters above the center. So this is saying the second bright maxima, so that's Y. Let's see, second bright above the center. Yeah, so the center is 0. The first one above would be 1, M equals 1. So center is M equals 0. First one above would be M equals 1. So this is Y2 that we're looking for, right? So they're saying Y2 is 25 millimeters. And we want to know slit separation. That's in for the double slit and for this diffraction grating, but for the double slit we call that D, so we want to know what is D. All right, so for brightness, for bright fringes or for maxima, we know that D sine theta has to be full wavelengths, M lambda, and so sine theta equals M lambda over D. And then we also know when we have the looking at the Y and the L and the theta, we know tan theta is Y over L, so Y is L tan theta. We can go ahead and use the small angle and say sine theta is equal to tangent theta, and so we can use the YM, make these YMs. YM is L sine theta equals L m lambda over d. Okay, and I just tend to not remember the exact equations, but if you have them on your equation sheet, you can use them. So in this case, we know y, where m is 2, y sub m is 25 millimeters, L is 2.5 meters, lambda is 600 nanometers, 10 to the negative 9 meters, and we're looking for D. All right, and so let's rewrite this. I got a mess. 25 times 10 to the negative 3 meters is y sub m equals L, 2.5 meters, times m, which is 2, times lambda, which is 600, times 10 to the negative 9 meters. All that divided by d is what we're looking for. Yes. So let's divide through by the 25 millimeters. That cancels, and multiply, and so divide through by 25 millimeters over here too. And then, yeah, divide both sides by 25 millimeters and multiply both sides by d. Those d's cancel, we get d over here. And so we get d equals 2.5 meters, that's L, capital L, times m, which is 2, 600 times 10 to the negative 9 meters, divided by the 25 millimeters. So d equals that, 2.5 times 2 times 600 e negative 9, all that divided by 25 e negative 3. 120 times 10 to the negative 6 meters. D is 120 micrometers. All right, sounds like a good small number. Sketch the setup including the interference pattern. All right, so we got our two little slits. This distance in there is D. And then we've got, probably not very well to scale, but we've got theta in here. We've got this distance is L. We've got this is the second bright fringe above. All right, so this distance Y2 is the 25 millimeters. Something like that. Okay. If the double slit is replaced by a single slit, find the second order minima, the second dark fringe, if the slit width is 10 micrometers. All right, so for a single slit, we have that A sine theta equals m lambda for dark minimum, right? Minima, something like that. Minima. Okay, find the second order minima. So find the second order minima. I think it's asking for y equals what? So y2 actually. Second order makes me think of m. So let's say m equals 2. When we say second order, m equals 2. Okay, again, we're going to use the y. Y is L sine theta, so in this case, y sub m, divide through both sides by a, and so is going to be L m lambda over a. Right, but we've got numbers up here, so L is 2.5 meters. M we said was 2, lambda is still 600 nanometers. We haven't been told it's different light, so we'll assume it's the same light. 600 times 10 to the negative 9 meters. And A, so the slit width is A, so it's 11 micrometers. Micro is 10 to the negative 6 meters. So we've got y sub m, m is 2, so let's just write it as y2 is all of that. So 2.5 6.5 times 2 times 600 e negative 9, all that divided by 11 e negative 6. 273 millimeters. Kind of big, but we'll go with it. 27 centimeters up, which is quite big for this, so maybe not very realistic numbers. Okay. But I think we did it right. Let me just double check my numbers from before. Looks good. Okay, part D. Find the diffraction angle now, so we want theta, for a second order maxima. So again, m equals 2, maxima, if the slit source is replaced, so slit's gone, with the diffraction grating. All right, so we've got diffraction grating, and we've got the slit spacing is 100 lines per millimeter. Okay, so for diffraction grating, the maxima are at d sine theta equals m lambda for full wavelengths, and we want theta in this case, so divide both sides by d, take inverse sine, so theta is going to be inverse sine of m lambda over d. Got to figure out d. So remember, we have the d is 1 over ss, but we've got to have the ss, the slit spacing for a diffraction grating. Remember, diffraction grating has a whole bunch of slits, right? Not just double slit, but many slits, right? 100 lines per millimeter kind of number. And so we've got 1 over 100 lines for 1 millimeter, but we need d to be in meters, so we need to convert this bottom to meters. So you got 1,000 millimeters is 1 meter, right? Cancel out this, and then we've got 1 over meters in the bottom of the fraction, so it's going to come out to be meters on the top. So d is going to be 1 over 100 times 1,000, and the unit's going to be meters. So let's do that. 1 divided by, put in parentheses, 100 times 1,000, just to make sure everything comes out right. So 10 times 10 to the negative 6 meters is d. Alright, so theta then is inverse sine of m, we said second order again, so 2 times lambda, 600 10 to the negative 9 meters, and then d is, in meters, is 10 times 10 to the negative 6 meters, so that's good, those cancel. So theta is, plug this in, inverse sine of, let's get some parentheses, 2 times 600 e negative 9, and that whole, that's the top, and divide that by 10 e negative 6. Yes, okay, so we get 6.89 degrees. Maybe we should call it theta 2. Anyway, it's the angle to the second order maximum. Did I get a number before? 6.9 degrees. Good. All right, so that is sample test 2.